In the beginning there was nothing, or so we think. A vast silent void stretching beyond comprehension. No stars, no matter, no time, just an infinite abyss. But what is nothing, really? Is it empty space, or something more elusive? Philosophers have long wrestled with this mystery. They ask, can nothing truly exist? If it does that mean it's something at all? Or is it simply the absence of everything, yet somehow still a concept we grasp? Scientists have dared to probe this dark frontier. Breakthroughs reveal a universe born from a chaos we could never fully understand. The very idea of nothing challenges our reality. Maybe in the end, nothing isn't the absence you imagine. Maybe it's the most profound presence of all, waiting to be revealed. As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. What does nothing truly mean in a philosophical context? It's a question that strips away the layers of everyday understanding and confronts us with the core of existence itself. When we say nothing, many of us imagine a void, an empty space devoid of matter, energy, or even space itself. But philosophers have long challenged this simplistic notion, revealing that nothing is far more complicated than it appears. At its most basic, nothing might seem like the absence of everything. No particles, no laws, no dimensions. It's the state before anything existed, or so we think. But is such a state even conceivable? Can we truly imagine a space where there is absolutely no thing, no potential, no possibility? That's where philosophers start to get tangled in paradoxes. To say nothing exists is to imply some sort of existence, since nothing is a concept we understand through contrast. Yet, questioning whether nothing can exist at all pushes us into questions about the nature of existence itself. Many thinkers argue that nothing is actually an unstable or impossible state. If there was truly nothing, then nothing could emerge or change. No cause, no potential, no laws of physics. But our universe, as far as we know, sprang from some sort of transition, from a state of nothing to a something. This leap raises profound questions. How can nothing give rise to something? Does nothing possess any kind of potential or power? Most philosophers would say no, that nothing is just a placeholder for the absence of being, rather than an active force or state of potential. Some modern philosophers and physicists, however, suggest that nothing might not be the absolute void we imagine, but rather a quantum vacuum, a state teeming with fluctuations where particles could pop in and out of existence. In that sense, nothing is not truly nothing but a kind of something in a very different form. This blurs the line between absolute void and something that resembles emptiness, but is still underpinned by quantum principles. So in the deepest philosophical sense, nothing is less about a literal absence and more about the boundary of human understanding, an idea that points to the limits of inquiry itself. It is the concept that haunts our curiosity about origins, pushing us to ask whether the universe's birth came from absolute nothingness or from something more subtle, more mysterious. Throughout human history, civilizations and philosophies have wrestled with the concept of nothing, each framing it in ways that reflect their unique worldview. To many ancient cultures, nothing was almost inconceivable, a blank slate or a void that was not supposed to exist at all. The Greeks, for example, approached nothing with a mixture of curiosity and skepticism. Aristotle famously argued that nothing was impossible, because the absence of everything is a non-being, and non-being cannot exist in any meaningful sense. Yet, he acknowledged that the universe had a Pythagorean significance, an underlying harmony, implying that nothing was more of a philosophical challenge than a reality. In contrast, the early Chinese Taoists saw nothing as an essential part of existence itself. The Tao, or the Way, was sometimes described as the nameless, an origin that precedes all things. Here, nothing was not a void or absence, but a dynamic potential, a fundamental principle that gave rise to everything. This perspective shifted nothing from a deficiency or emptiness to a fertile ground, a sort of passive fullness that embodies the unity of all existence. In Indian philosophy, particularly within Vedanta, nothing takes on a different flavour. It's often connected with the concept of shunyata, or emptiness, especially in Buddhist thought. Shunyata is not mere nothingness. Rather, it signifies the absence of intrinsic separate existence in all phenomena. It emphasizes the emptiness of the universe from independent, unchanging essence, and points toward an interconnected, fluid existence that dissolves the boundary between being and non-being. In the Western medieval Christian tradition, nothing was often considered in theological terms. The divine act of creation turned nothing into something. Before creation, there was in Christian doctrine a void or chaos, a formless darkness, where nothing held a shadowy, pre-creation significance. It was a state of potential, something that God brought into existence through divine will, transforming nothing into the cosmos. Meanwhile, in more recent philosophical debates, especially in existentialism and modern science, nothing is a much more complex and nuanced idea. Some thinkers claim that nothing is an active, almost creative force, an emptiness that sparks transformation, while others see it as a philosophical puzzle that highlights the limits of human understanding about the universe's origins. These diverse perspectives echo through history, revealing that nothing isn't simply the absence of everything. It's a reflection of how we interpret existence itself. The concept of nothing is fundamental to understanding the origin of the universe because it challenges our deepest intuitions about existence and reality. When we think of the universe's beginning, we're often tempted to imagine a sort of pre-existing void, an empty space that somehow transitioned into something. But truly grappling with nothing forces us to confront whether such a state was genuinely devoid of anything, without particles, energy, space, time, or even potential. Without thoroughly examining nothing, we risk falling into misconceptions. For instance, it's easy to assume that the universe emerged from some sort of something, a pre-existing material or energy, rather than from absolute non-existence. However, modern physics suggests that the universe might have originated from a state that defies classical understanding, a quantum vacuum, a condition that isn't quite empty in the traditional sense, but rather a seething froth of potentialities. Still, this raises questions about whether this quantum nothing truly qualifies as nothing, or if it is in fact a different kind of something. Understanding nothing also illuminates why the question "why is there something rather than nothing?" has puzzled humans for centuries. If nothing truly existed, what could instigate the transition to something? Does the universe's existence imply some underlying necessity or a fundamental flaw in the idea of ultimate nothingness? Or is the universe an exception to the rule that nothing is the natural state? These are profound questions because they go to the heart of causality, contingency, and necessity. Furthermore, exploring nothing connects to the concept of the vacuum state in quantum physics, where fluctuations can create particles out of seemingly nothing. This suggests that, at least in physics, nothing isn't merely the absence of everything, but a state with potentialities. Recognizing the difference between philosophical nothing, absolute non-being, and the quantum vacuum helps us appreciate that the origin might involve a transition from one form of nothing to a different state that appears as something. Ultimately, the importance lies in whether nothing is truly a possible starting point or merely a conceptual placeholder. Understanding this shapes our entire narrative about cosmic origins, forcing us to reconsider what it means for something to come from nothing, and whether such a concept is even coherent. When we grapple with nothing, we are in fact testing the very limits of what existence entails. From a scientific standpoint, the concept of nothing is less about an absolute void and more about a state devoid of matter, energy, and even space itself. Physicists often describe it as a quantum vacuum, a restless energetic sea where particles continually pop in and out of existence. This might sound like a contradiction. How can nothing be filled with something? Yet on the quantum level, zero energy does not necessarily mean complete emptiness. Instead, it's a frothing, dynamic background where physical laws still hold sway, governed by probabilities and fluctuations. In this light, nothing isn't a simple absence, but a complex, unstable condition from which our universe could emerge. Current theories, like the Hartle-Hawking state, suggest that before the Big Bang, there was a kind of timeless quantum foam, a fluctuating field that defies traditional notions of existence or non-existence. Contrast this with philosophical and theological views, where nothing often carries deeper existential and metaphysical implications. Philosophy might ask whether nothing is even a coherent concept. Can anything truly be nothing, or is that an impossibility? Some thinkers argue that nothing is an illusory concept, because even in complete absence, some form of being or potentiality remains. Theologians, on the other hand, frequently link nothing to the divine or to a state before creation, a void from which a supreme being brought everything into existence. In this perspective, nothing is not just a physical state, but a moral or spiritual void, a blank canvas awaiting the divine act of creation. Yet, both philosophies and religions tend to see nothing as a mysterious and perhaps ungraspable concept, something that transcends human understanding. They often invoke a realm beyond physical explanation, a spiritual or divine origin that isn't limited by scientific definitions. While science seeks to explain the origins of the universe through measurable, testable phenomena, philosophy and theology grapple with questions about existence that often go beyond what empirical evidence can reveal. In essence, science approaches nothing as a state describable in the language of physics, an energetic, quantum, fluctuation-rich platform. Philosophy and theology, however, view nothing as a profound metaphysical mystery, a void that holds within it the seeds of all that exists, or a state beyond comprehension entirely. The Big Bang Theory is the leading explanation for how our universe came into existence. It suggests that everything we see around us, stars, planets, galaxies, and even space itself, began as an incredibly hot, dense point roughly 13.8 billion years ago. Picture all of the universe squeezed into a tiny, infinitely small point, so small and so dense that our usual understanding of space and time breaks down. This initial state is often called a singularity, although in reality, it's more of a boundary where our current physics cannot fully describe what happened. From this primordial state, a rapid expansion took place, what scientists call the Big Bang. As it expanded, the universe cooled down, allowing particles to form and eventually combine into atoms. These atoms gathered and clumped together under gravity's influence, forming the galaxies, stars, and planets that fill the cosmos today. Think of it as a kind of universal balloon inflation, but instead of just the surface stretching, the fabric of space itself was expanding outward, carrying everything along with it. The Big Bang Theory doesn't just describe a sudden explosion in space, it illustrates that space and time themselves are intertwined, and that both began at this moment of rapid expansion. Before the Big Bang, according to the theory, there was no before in the way we understand time. No past or future, just this singular beginning. Scientists support this model through a range of evidence. One key piece is the observation that galaxies are moving away from us in all directions. If you think of raisins in a rising loaf of bread, as the dough expands, every raisin gets farther apart. Similarly, the increasing distance between galaxies suggests that the universe has been expanding since its earliest moments. Then there's the cosmic microwave background radiation, and faint glow permeating the universe, like a baby picture of the cosmos, perfect evidence of the heat from the universe's hot beginnings. Another cornerstone for the Big Bang is the relative abundance of light elements like hydrogen and helium, which matches what our models predict about the universe's first minutes. When scientists crunch the numbers, they find that everything fits neatly into this expanding, cooling universe scenario. The Big Bang is a powerful framework, but it also raises profound questions. What caused the initial expansion? What was before the singularity? How does it connect to theories of quantum mechanics and string theory? As much as it helps us understand where we came from, it opens even more doors for curiosity, pushing us to consider what lies beyond our current understanding. When it comes to evidence supporting the Big Bang theory, the universe itself offers a cosmic detective story, full of clues pointing back to a fiery beginning. One of the earliest and most compelling pieces is the observation of the universe's expansion. Astronomer Edwin Hubble in the 1920s measured the redshift of distant galaxies, a phenomenon where light stretches out, shifting toward the red end of the spectrum. This redshift indicates these galaxies are moving away from us, and the farther they are, the faster they seem to recede. It's as if the universe itself is stretching, like a loaf of raisin bread rising in the oven. The implication? The universe was once densely packed in a tiny hot state, expanding outward over billions of years. Another key piece of evidence is the cosmic microwave background radiation. Discovered in 1960, this faint glow of microwave energy is the afterglow of the early universe, a residual heat from the Big Bang itself. Imagine an enormous universal oven that, after billions of years, still radiates heat. This radiation is remarkably uniform across the sky, bearing the imprint of an incredibly hot, dense cosmos just moments after its birth. Its existence not only supports the notion of a hot, dense origin, but also provides a snapshot of the universe in its earliest moments. Then there's the relative abundance of light elements like hydrogen, helium, and lithium. The proportions of these elements in the universe match the predictions made by Big Bang nuclear synthesis models, which describe how these elements formed within the first few minutes after the universe's inception. The specific ratios, such as about 78% hydrogen and 22% helium, are like fingerprints, aligning perfectly with what the Big Bang theory predicts. Finally, large-scale structures, clusters of galaxies and their distribution, tell a story. Computer simulations based on the Big Bang model have successfully recreated the web-like cosmic structure we observe today, from galaxy filaments to voids. It's as if the universe's very blueprint was written during its earliest moments. All of these clues come together, forming a compelling mosaic that makes the Big Bang theory not just a hypothesis, but the most robust explanation we have for the universe's origins. When cosmologists talk about the early state of the universe, they're referring to a period so distant in time that it stretches the limits of human imagination. It's like peering back across billions of years, trying to understand what that universe, or perhaps what nothing, looked like at its very inception. According to the prevailing scientific view, the early universe was an unimaginably hot and dense point, often called a singularity, where our current understanding of physics breaks down. But that doesn't mean it was nothing. Rather, it was a state of almost incomprehensible energy packed into an incredibly tiny space. In the earliest moments after the Big Bang, the universe went through a rapid exponential expansion known as inflation. During this period, the universe's size skyrocketed faster than light, stretching quantum fluctuations into the vast cosmic structures we observe today. The universe was a hot, dense plasma of particles, protons, neutrons, and electrons, moving at relativistic speeds. At this stage, temperature and density were so extreme that ordinary matter as we understand it couldn't even exist. Cosmologists often describe this early epoch with the language of theoretical physics, tools like quantum field theory and general relativity. But as we push further back in time, models suggest that space, time, and the fabric of the universe itself may have been born from a state where classical notions don't apply. Instead of imagining a pre-existing nothing, scientists contemplate that space and time could have emerged from a quantum foam, an ultra-turbulent fluctuating fabric of space-time, where uncertainties reign supreme and classical physics yields to quantum weirdness. This leads us to profound questions. Was there truly a before the Big Bang? Or does the universe just pop into existence from a realm beyond our grasp? Something that might be better described as a quantum fluctuation, or a transition from a different state altogether. As cosmologists probe the earliest moments, they're confronted with the limits of scientific knowledge, where equations break down and speculation takes the stage. Ultimately, the early universe isn't just a simple beginning, it's a complex puzzle, blending physics, philosophy, and perhaps something more mysterious. Despite the incredible progress scientists have made in understanding our universe, there are still significant limitations when it comes to explaining its very beginning. Our current models, while powerful, are like maps that guide us through known territory, but leave many mysterious uncharted regions. For example, the Big Bang theory describes how the universe expanded from an extremely hot and dense state roughly 8 billion years ago. It provides a compelling narrative for the universe's evolution after that initial moment, but it offers little insight into what actually triggered that event, or what, if anything, came before. One major limitation stems from the fact that our understanding of physics breaks down under extreme conditions that existed at the very moment of the Big Bang. When we try to combine quantum mechanics, which governs the tiny subatomic world, with general relativity, the theory governing gravity and the large-scale structure of space-time, the equations become incompatible. This clash prevents us from developing a coherent theory of quantum gravity that could describe the universe's birth at the smallest scales and highest energies. Another obstacle lies in the horizon problem. Since distant parts of the universe are not in causal contact, meaning they couldn't have exchanged information or influence, how did they come to have such remarkably uniform temperatures? Current models rely on a process called inflation, a rapid exponential expansion that supposedly smoothed out the universe's initial irregularities. But the origin of inflation itself and what prompted this rapid expansion remain unresolved mysteries. We lack a definitive physical mechanism explaining its onset and halting, leaving room for speculation and unanswered questions. Additionally, the concept of initial conditions adds to the uncertainty. Our models often assume a set of initial parameters, but they don't explain why these conditions existed in the first place. Are these conditions unique, or could they be part of a broader multiverse where different regions have different histories? The multiverse idea stretches the limits of testability, making it difficult to verify with empirical evidence. These limitations remind us that, even with our most advanced theories, we're still peering into a fog of the unknown. The true origin of the universe might involve phenomena beyond our current scientific reach, concepts that challenge or even transcend the very fabric of our understanding. Quantum mechanics paints a picture of the vacuum that's far more dynamic and strange than our everyday experience suggests. To most of us, a vacuum might seem like empty space, a void devoid of anything. But on a quantum level, the vacuum is anything but empty. It's a bubbling, restless fabric filled with tiny, fleeting energy fluctuations that constantly pop in and out of existence. Imagine the calm surface of a pond, perfectly still. Now picture beneath that surface an unseen eddying current, tiny ripples, minuscule whirlpools that are happening all the time, even when the pond seems perfectly calm. That's somewhat like what quantum fluctuations are for the vacuum. Quantum theory tells us that due to the uncertainty principle, an idea that's fundamental to the theory, certain pairs of properties, like energy and time, can't both be known exactly at the same moment. This means that the vacuum can't be a state of perfect, unchanging emptiness. Instead, it is a seething foam of energy, where particles of matter and antimatter spontaneously appear and vanish, all within fractions of a second. These particles are known as virtual particles, and although they cannot be directly observed, they influence the universe in profound ways. One striking way quantum mechanics describes the vacuum is through the concept of zero-point energy, the lowest possible energy that a quantum system can have, even when it is at rest. No matter how much you cool down an object, this zero-point energy persists. Think of it like the faint hum of a radio even when it's turned off, the background noise that can't be fully eliminated. In the vacuum, this energy manifests as a constant, unpredictable flickering, a kind of restless energy that is fundamental to the fabric of space itself. This quantum froth isn't just theoretical musing, it has measurable consequences. For example, the Casimir effect demonstrates how two uncharged metal plates placed very close together in a vacuum can be pulled toward each other due to this quantum fluctuation. The plates are essentially responding to the change in the energy of the vacuum between them compared to outside, a tangible reminder that the vacuum's emptiness holds hidden complexity. In this quantum view, the universe's fabric is much more alive and interconnected than our everyday intuition suggests. The vacuum isn't a simple emptiness waiting to be filled, it's a dynamic stage, constantly fluctuating with energy and particles, shaping the very structure of reality at the smallest scales. It's almost poetic to think that the void, which might be thought of as nothing, is actually packed full of restless potential, a cosmic seedbed of possibility itself. Quantum fluctuations are tiny, almost unimaginably brief changes in energy that occur everywhere in the universe at the smallest scales. Imagine the fabric of space itself as a restless, bubbling sea, where particles and antiparticles wink in and out of existence in the blink of an eye. These fluctuations are not just quirks of the quantum world, they are fundamental to how the universe behaves at its most basic level. In fact, they are so pervasive that they can seed the formation of galaxies, stars, and planets from a seemingly featureless void. But how do they relate to the idea of nothing? That's where things get mind-bending. When we talk about nothing in classical terms, we usually mean an absolute void. No matter, no energy, just emptiness. Yet quantum physics suggests that what we call nothing isn't truly nothing at all. Instead, it's a frothing, lively state, filled with these ceaseless fluctuations. In this quantum realm, the concept of nothing morphs into something more like a seething energetic backdrop, an almost impossible idea to grasp but essential for understanding the universe's potential origins. Some physicists theorize that these quantum fluctuations could have played a critical role in the birth of everything. What if, in that quantum froth, a fluctuation was large enough to create a tiny pocket of energy that then expanded exponentially, giving rise to the universe we inhabit today? This idea suggests that nothing, in the quantum sense, isn't a void at all, but a dynamic episode, a restless canvas where the seeds of reality are sown in spontaneous, unpredictable moments. This perspective challenges our intuition. It implies that the universe might have emerged from a bubbling quantum state that devasts classical notions of emptiness. Instead of a perfect vacuum, we get a vibrant, restless quantum nothing, where fluctuations ripple outward, setting the stage for the universe's grand unfolding. The whole story invites us to rethink what nothing really is, revealing it as a potential wellspring of everything rather than a simple absence. The idea that the quantum vacuum can give rise to particles, or even an entire universe, is one of the most mind-bending concepts in modern physics. At first glance, the word vacuum suggests emptiness, a void devoid of everything. But in the quantum realm, emptiness is far from silent or empty in the traditional sense. Instead, it's a seething, bubbling sea of potentiality, a stage where particles continuously flicker into and out of existence in fleeting quantum fluctuations. These ephemeral particles pop into existence for tiny fractions of a second before vanishing again, a dance driven by the uncertainty principle. Now, some scientists propose that these quantum fluctuations could be more than just brief blips. Perhaps they could ignite the birth of a universe. How could that happen? Imagine this quantum vacuum as a sort of cosmic seed bed. When a fluctuation becomes enormous enough, it might stretch space itself, creating what's known as a bubble of inflating space. This is akin to a tiny universe sprouting from a quantum ripple. Over time, this bubble could grow, evolve, and become the universe we see today. The idea is supported by models of cosmic inflation, where a quantum event triggers an exponential expansion of space-time, smoothing out irregularities and setting the stage for galaxies to form. From this perspective, our entire universe could be just one of countless bubbles in a vast multiverse, each born from quantum turbulence. But here's where things get even more fascinating and perplexing. Is this process just a speculative hypothesis, or does it have a solid footing in physics? While we have indirect evidence suggesting quantum effects shaped the early universe, directly proving that a quantum vacuum birthed a universe remains elusive. The boundaries of current knowledge prevent us from fully testing these ideas, leaving us with tantalizing possibilities and profound questions. If particles can emerge from nothing, and indeed entire universes can bubble into existence from quantum froth, what does that say about the nature of reality itself? Could nothing truly contain the seeds of everything? That mystery continues to challenge, inspire, and redefine our understanding of existence. Quantum phenomena force us to rethink what nothing really means at its most fundamental level. When physicists talk about nothing, they're often describing a vacuum, a space devoid of matter and energy. But in the quantum world, this emptiness is anything but empty. Instead, it teems with activity and potential. Particles are constantly popping into and out of existence in fleeting quantum fluctuations, tiny blips of energy that challenge our classical ideas of nothingness. These fluctuations imply that the vacuum isn't truly empty, but is instead a seething, dynamic field. If even empty space is alive with temporary particles and energy, then the universe itself may have emerged from this quantum froth. It's as if nothing contains within it the seeds of everything, an energetic playground from which matter, energy, and even space-time could spontaneously arise. This realization shakes the concept of absolute nothingness to its core. Instead of imagining a complete void, we're led to consider a baseline of quantum potential, a condition of nothing, rich with possibility. It suggests that our universe might be one of countless others born from these quantum fluctuations, each popping into existence in a vast, ever-changing quantum landscape. The implications ripple beyond physics into philosophy. If nothing isn't really nothing, then the question of why there is something rather than nothing might need to be rephrased. Perhaps the universe doesn't need a creator or a purpose. It could be the natural consequence of quantum laws embedded deep in the fabric of space-time. In this view, nothing is actually the stage loaded with hidden potential, waiting to be triggered by the strange probabilistic dance of quantum mechanics. Understanding these quantum phenomena pushes us to abandon our classical notions of emptiness and explore a universe where nothing isn't void, but a fertile ground for creation. It's a shift from seeing nothing as a simple absence to recognizing it as a vibrant foundation from which all existence might emerge. When discussing the universe's origins from nothing, we enter a realm where physics and philosophy intertwine, creating a tapestry of ideas. One prominent hypothesis is that of quantum fluctuation. In the subatomic world governed by quantum mechanics, the vacuum isn't truly empty. Instead, it's a bubbling foam of energy, where particles spontaneously appear and vanish in moments too fleeting to observe. Some scientists propose that the universe could have begun as a tiny quantum fluctuation, a brief ripple in the fabric of space-time, arising from this restless vacuum. In this view, nothing isn't a static void, but a dynamic, probabilistic field filled with potential. From this fluctuation, the universe could have bubbled into existence, then expanded into the cosmos we observe today. The challenge lies in understanding how such a process is mathematically and physically possible, how a fluctuation could evolve into an entire universe. Another hypothesis stems from cosmic inflation and the multiverse concept. Some theories suggest our universe is just one bubble in an ever-growing foam of universes, each emerging from similar quantum events. Imagine an infinite, perhaps almost nothing-like backdrop giving rise to countless universes through fluctuations or phase transitions. In this multiverse scenario, our universe's emergence was merely one such event, originating from the fabric of space-time itself. The question of true nothingness becomes more complex here. If these bubbles arise from a pre-existing multiversal sea, can we truly say they originate from absolute nothing? Or is there an underlying substrate mysterious in nature? Some ideas go even further, proposing the universe could have originated through a tunneling process. Think of a cosmic leap, similar to quantum tunneling, where the universe jumps from a low-energy state into a vast, expanding cosmos. This concept borrows from quantum mechanics, where particles surmount barriers deemed impenetrable by classical physics. In cosmological terms, the universe might have tunneled out of a quantum state akin to nothing, not empty, but a state of pure potential. Such a process suggests nothing isn't classical emptiness, but a state of unstable, unformed potential awaiting realization. Other theories propose the universe emerged from a pre-existing quantum or hyperdimensional space. Some believe what appears as nothing might actually be a higher dimensional framework or quantum gravity realm, an exotic, inaccessible level of reality. In this view, our universe's birth is comparable to a bubble forming in a higher dimensional fabric with nothing, perhaps, an incomplete description of a deeper reality. All these ideas stretch human understanding, challenging the very concept of nothing. Is it a true void or something more subtle, a quantum ocean of potential with hidden depths? As science advances, perhaps we will peel back these layers, revealing whether nothing truly existed before the Big Bang, or if such questions are based on a misunderstanding of the universe's true nature. The idea of a universe emerging from quantum nothing fundamentally challenges the traditional classical notions of creation and existence. For centuries, people have believed that something must have always existed, or that a divine force created everything from a void. These ideas are rooted in a worldview where nothing is simply the absence of anything. No matter, no energy, no space, no time. It's a clean slate, a perfect vacuum, ready to be filled or created by a supreme act. But in the quantum realm, the concept of nothing takes on a much more nuanced meaning. Here, nothing is not just an empty void. Instead, it's a seething froth of potential energy, fluctuating fields and probabilistic possibilities. Quantum field theory shows us that even in a vacuum, what we might think of as nothing, particles constantly pop in and out of existence due to quantum fluctuations. This suggests that nothing isn't static or sterile, but dynamically active, filled with possibilities waiting to materialize. This radically redefines the classical idea of a complete void. If the quantum vacuum isn't nothing in the traditional sense but rather a realm of potentialities, then the universe's emergence from it isn't quite the same as creation from absolute nothingness. It's more like a sculptor shaping reality from a clay that's already there, albeit in a very subtle, energetic form. It's as if the universe didn't need an external spark or divine intervention to come into being. Instead, it might have arisen from intrinsic quantum tendencies embedded within the very fabric of reality. Furthermore, this challenges the notion that the universe had a definitive beginning, implying instead that what we perceive as creation could be a transition from a state of quantum potentiality to classical existence. It pushes us to consider that time and space themselves may have emerged out of this quantum bubbling, a process that defies straightforward causal explanations rooted in classical physics. So the idea of a universe born from quantum nothing doesn't just stretch our scientific understanding, it confronts the philosophical and metaphysical foundations of how we conceive existence itself. It invites us into a realm where nothing isn't empty, but full of untapped possibility, reshaping the very narrative of origins in the cosmos. Quantum tunneling opens up an intriguing possibility when it comes to understanding how our universe might have come into being from what we call nothing. Imagine a landscape filled with valleys and hills. These represent different states or configurations that the universe could assume. In classical physics, if you don't have enough energy to overcome a barrier, you're stuck on your side. But in quantum mechanics, particles have a strange ability. They can occasionally tunnel through barriers, even if they don't have enough energy to surmount them. This concept takes on a cosmic scale in the hypothesis of quantum tunneling in cosmology. Instead of particles, think of the universe itself as a quantum system. The idea proposes that our universe could have tunneled from a state of nothing, a sort of quantum vacuum, into an expanding universe. It's as if the universe made a leap across a barrier that classical physics would deem insurmountable. This tunneling event could have triggered the sudden birth of space and time as we know them. The fascinating part is that this nothing isn't the simple absence of everything we picture. Instead, it's thought to be a highly unstable quantum fluctuating state, filled with potential. This state might have had tiny, quantum-scale fluctuations, those tiniest of jitters, that somehow allowed the universe to pop into existence through tunneling. The process bypasses the need for a pre-existing cause. Rather, it's a spontaneous leap into a new configuration. Physicists develop models like the Hartle-Hawking no-boundary proposal, which suggests that the universe could have tunneled from a state without boundaries or edges. From this perspective, nothing isn't a void, but a sort of quantum foam or field of possibilities. Once the universe tunneled through that barrier, it would begin to expand and evolve, giving rise to galaxies, stars, and all the complex structures we observe today. It's both a mind-bending concept and one that offers a potential answer to the ultimate question of origin. Could our entire universe have begun with a quantum leap, springing from a state that wasn't quite nothing, but rather an energetic sea of potential waiting to be realized? That's the compelling possibility this hypothesis presents. Some scientific models explore the idea that the universe didn't require an initial physical state, challenging traditional notions of a beginning. Instead of asking what existed before the Big Bang, these models propose that there's no need for a prior cause or a definitive initial condition. They envision a scenario where the universe, or multiverse, emerges spontaneously, without emerging from a pre-existing state in space or time. One prominent idea involves quantum fluctuations arising from a state of nothing. In quantum mechanics, the concept of a vacuum isn't empty, but filled with potentialities and virtual particles that pop in and out of existence. These fluctuations can, in principle, produce particles or even entire universes without a cause, since quantum events are inherently probabilistic. The universe might have materialized from this quantum vacuum, a seething field of possibilities, not as a result of a cause but as part of the inherent randomness allowed by quantum laws. In this view, nothing isn't absolute emptiness, but a delicate landscape of potentialities that spontaneously generate a universe without a triggering event. Another approach considers models involving a multiverse, a vast, possibly infinite ensemble of universes. These universes could originate from a broader, timeless structure where no single creation event is necessary. Instead, they continually branch or fluctuate within this overarching framework. Here, the multiverse exists in a state that defies classical notions of cause and effect, making before or initial nonsensical concepts. Such models imply that our universe is just one of countless bubbles or branches emerging from a more fundamental, unchanging reality, which itself has no starting point. These theories challenge the assumption that everything must have a cause or a beginning. They suggest that the cosmos might be eternal or cyclical, with no true nothing preceding it, but rather a domain of infinite potential or a boundary-less multiversal fabric. This conceptual shift means the question of what came before the Big Bang may be meaningless, because in these models, time and causality as we understand them may not apply at the moment of universe's origin. Philosophical traditions around the world have long wrestled with the idea of nothing in relation to creation, often seeing it as a profound and fundamental question about the origins of existence itself. In Western philosophy, especially in ancient Greece, thinkers like Parmenides challenged the notion of nothing, arguing that nothing simply cannot exist, because to speak of it is to assign it being or existence in some form. For Parmenides, reality was an unchanging, eternal being, and the concept of non-being was impossible to genuinely conceive. Conversely, Heraclitus believed that everything was in a constant state of flux, and that nothing was perhaps more akin to a precursor state, an empty chaos from which the order of the cosmos emerged. Venturing into religious philosophies, many traditions see creation as emerging from a state of absolute nothing. In Christianity and Islam, for example, the divine acts of creation often transcend human logic, suggesting that God's act of bringing forth the universe was not from something, but from a divine act of utteral nothingness. In these views, nothing is not just emptiness, but a backdrop that allows the divine to bring everything into existence, emphasizing the creative power lying beyond the confines of matter and form. In Eastern philosophies, especially in Vedanta and Taoism, nothing is sometimes interpreted as shunyata, a void or emptiness that is not merely the absence of things but a fundamental reality underlying all existence. This emptiness isn't bleak or nihilistic. Rather, it is a fertile ground for creation and transformation. The Tao, or the Way, flows from this emptiness, suggesting that the origin of everything is rooted in a dynamic potential that exists in nothing. Many philosophical traditions also examine the paradox of nothing as a beginning point. If everything comes from nothing, then nothing must have some sort of capacity or potentiality inherently. This leads to intriguing questions about whether nothing is a state of pure potential, a void filled with unmanifested possibilities, or simply beyond human comprehension. The common thread through these diverse views is an acknowledgement that nothing holds a special role in the mystery of creation, neither purely negative nor entirely void, but a pivotal concept that continues to challenge and inspire our understanding of existence's origins. The theological perspective on nothing before creation is a fascinating realm of thought that offers a stark contrast to scientific and philosophical explanations. Many religious traditions suggest that before the act of creation, there was not just emptiness or chaos, but a state of absolute non-being, an absence so complete that it defies human comprehension. To some, this nothing is not merely the absence of matter or energy, but a profound void that existed prior to divine intervention or divine will. In many monotheistic faiths, especially within Christianity, Judaism, and Islam, the concept of creation begins with the divine. God exists outside of time and space, unbound by the limits of physical reality. When these traditions speak of creation from nothing, they use the Latin term creatio ex nihilo, creation out of nothing. Here, nothing isn't just empty space, but a state of non-existence that only God's creative power can bring into being. This perspective emphasizes that the universe didn't emerge from a pre-existing chaos or matter, but from a divine act that transcends physical reality altogether. In this view, the void before creation isn't a starting point in time, but a non-entity that only the divine can bring into existence through will and word. Some theological narratives go further, describing nothing before creation as an act of divine silence or mystery, a space where nothing exists except the divine essence itself. It's a state beyond human understanding, emphasizing that the origins of the universe are rooted in divine sovereignty rather than physical processes. This underscores the belief that the universe is ultimately a manifestation of divine purpose, not an accidental or inevitable event, and that the nothing before creation was an active, intentional nothing, a blank canvas awaiting divine action. In fewer words, many theological views highlight that nothing before creation isn't just emptiness, but a profound mystery, an active blank slate that only a divine being, infinite and beyond human grasp, could bring forth into existence. It's a reminder that even before the universe existed, there was a divine breath, a divine thought, shaping the potential for everything that would come into being. The philosophical, theological, and scientific perspectives on nothing may seem to be speaking different languages, but they often intertwine in fascinating ways. Philosophers have long pondered the nature of nothingness, raising questions about whether truly nothing can exist, or if even emptiness is itself a sort of something, filled with potentialities or underlying structures we can't perceive. They challenge us to think beyond the visible and question whether our concept of nothing is just a human construction, a boundary of understanding rather than an absolute state. Theologically, many traditions present nothing as an absence or void from which a divine act brought everything into existence. This idea can seem to conflict with scientific views that look for natural, physical explanations rooted in the laws of physics and quantum mechanics. Science, on the other hand, tends to define nothing as a state of empty space, albeit one that is brimming with quantum fluctuations and virtual particles. It's a dynamic, restless void, not a perfect emptiness, but a seething reservoir of potentialities that can give rise to stars, planets, or even entire universes through processes like quantum tunneling. In this framework, the universe's origins aren't necessarily rooted in a divine act, but in spontaneous probabilistic events within a quantum framework. Yet, these scientific explanations often seem to brush against philosophical questions about whether such a quantum vacuum is truly nothing, since it has structure and potential. There are points of both conflict and convergence. They collide when philosophical notions of absolute nothingness clash with scientific descriptions of quantum fields that are anything but empty in the classical sense. At the same time, they converge in the realization that our understanding of the universe's origin is incomplete and deeply complex. Both perspectives push us to recognize that nothing isn't as straightforward as it sounds. Philosophy asks what nothing really means, while science tries to find mechanisms that could have produced the universe from a state that might be called nothing. In that space between belief and evidence, between inquiry and interpretation, we see a vivid picture emerging, one where the boundaries of nothing and something blur, compelling us to explore deeper into the true nature of existence itself. Can modern science truly reconcile with the philosophical or religious notions of creation from nothing? That question sits at the crossroads of science, philosophy, and faith, challenging us to examine what nothing really means in each context. Philosophers have long debated whether nothing is a meaningful concept at all. To some, nothing isn't just emptiness, but an absolute void, a state devoid of anything, including space, time, and even potentiality. Others suggest nothing might be an unstable or fleeting condition, perhaps just a philosophical construct rather than a physical reality. Religious traditions often describe creation ex nihilo, out of nothing, in a divine act, emphasizing a purposeful beginning originating from a divine will rather than randomness. Modern physics complicates this picture. When scientists speak of the origin of the universe, they often describe it emerging from a quantum vacuum, a state filled with fluctuations, potentialities, and fleeting particles apparent in quantum field theory. This vacuum isn't exactly nothing in the traditional sense. It's a seething energetic backdrop teeming with transient phenomena. These quantum fluctuations can, under some models, give rise to entire universes through processes like quantum tunneling. Here, the boundary between nothing and something becomes blurred, challenging the classical conceptions of a true void. Some physicists argue that the universe might have emerged from a state of no boundary, a concept proposed by Stephen Hawking and James Hartley, where asking what came before the Big Bang becomes a meaningless question because time itself begins at that point. In this view, nothing isn't a pre-existing emptiness, but a condition where the usual notions of time and space break down, merging into a sort of quantum foam. Despite these scientific insights, the reconciliation with religious or philosophical ideas isn't straightforward. While science offers mechanisms, quantum fluctuations, inflationary models, multiverses, these do not necessarily address purpose or intention. Many faith traditions see creation as an act of divine will, something fundamentally different from the probabilistic and mechanistic explanations science provides. Rather than fully reconciling, science and religion sometimes speak different languages, science describing how the universe came into being, and religion pondering why it exists at all. For some, this divide deepens the mystery, leaving open the possibility that nothing might be more than just a scientific concept, perhaps a profound philosophical or spiritual truth waiting to be understood. Trying to pinpoint the origins of nothing is like venturing into a vast, uncharted wilderness, full of unknowns, paradoxes, and contradictions. On the scientific side, one of the toughest hurdles is the very definition of nothing. Traditionally, scientists think of it as a vacuum, a space devoid of matter, energy, and even particles. But quantum physics throws a wrench into that concept. What appears as emptiness isn't truly empty. Instead, it's a seething froth of temporary particles flickering in and out of existence due to quantum fluctuations. Trying to describe this quantum vacuum as nothing becomes tricky because it's actually brimming with activity. So the question emerges, can the quantum vacuum truly be called nothing? Or is that a misunderstanding stemming from classical intuition? Moreover, the mathematics involved in describing the universe's birth from nothing often requires conditions or parameters that themselves lack explanation. For example, models like quantum tunneling or the Hartle-Hawking state propose that the universe could have popped into existence from a state without a boundary. But they rely on assumptions that push the boundaries of human understanding. What was before the universe, if anything, and what are the physical laws governing that state? These are questions that current physics can't fully answer, partly because they occur at the edges of our knowledge, at scales and energies where our theories break down. Philosophically, the challenges are even more perplexing. Many philosophies have wrestled with the notion of nothing. Is nothing merely the absence of everything, or does it have some sort of potential? Some argue that nothing can't exist at all, because even the idea of nothing presupposes the concept of something. There's a paradox. How can the state of absolute non-being give rise to being itself? This pushes us into the core of metaphysical debates. Does something always have to exist, or can nothing be a true stable state? If nothing is unstable, does that imply that the universe's existence is inevitable, or is the universe a random occurrence that defies every attempt at ultimate explanation? Adding to the challenge is the problem of human understanding. Our minds are wired to think in terms of existence and causality. The concept of nothingness defies these instincts. It's so far removed from everyday experience that grasping it feels almost impossible. How can we even conceive of a state that contains no laws, no particles, no space, no time? These philosophical and scientific puzzles aren't just academic. They challenge the very foundation of how we perceive reality, threatening to rewrite what we think we know about existence itself. Future discoveries in physics and cosmology could significantly reshape our understanding of nothing and cosmic origins. Advances in quantum mechanics may uncover principles bridging the virtual vacuum and the emergence of space and time, revealing that nothing is a dynamic foam of energy fluctuations. This could suggest the universe didn't arise from absolute emptiness, but from a state rich with potentialities governed by laws yet to be understood. Next-generation telescopes and observational tools will explore deeper into the universe's infancy, potentially capturing signals that predate the Big Bang, such as remnants of a cosmic bounce or signatures of multiverse interactions. Detecting gravitational waves from an earlier epoch could provide clues about processes that triggered our universe's birth, indicating origins from higher dimensional space, brain collisions in string theory, or other exotic scenarios. On the theoretical side, new models may unify quantum mechanics with general relativity, resolving paradoxes related to singularities and initial conditions. A successful theory of quantum gravity might shift our view from a universe arising from nothing to one emerging from quantum potentiality, a primordial quantum field that defies traditional notions of existence or non-existence. Furthermore, exploring the multiverse hypothesis might show our universe is just one bubble among many, each with distinct physical constants. This concept implies nothing could be a layered idea, with our universe being a rare fluctuation within an infinite landscape of possibilities. All these lines of inquiry are connected by the fundamental question: is nothing truly nothing, or a form of something we are only beginning to understand? As technological and theoretical advancements progress, insights may emerge that challenge or redefine the very nature of existence. The pursuit of knowledge continues to push the boundaries of what we know about the origins of the universe, and perhaps even about the essence of nothing itself. Ultimately, future discoveries may reshape our foundational understanding of reality. When it comes to probing the origins of the universe from nothing, science faces a unique challenge. After all, how do you test something that by definition was beyond the realm of our observable universe and conventional measurement? Still, physicists have devised some clever approaches to explore these profound questions, trying to find clues within the fabric of our current universe. One approach is through the study of cosmic microwave background radiation, the faint glow of energy left over from the universe's earliest moments. Slight fluctuations in this ancient light carry messages from the universe's infancy, potentially offering insights into its birth from a quantum fluctuation or a transition from a nothing state. By meticulously analysing these variations, scientists hope to reveal patterns or anomalies that could support or challenge models like the quantum tunneling hypothesis, where the universe emerges spontaneously from a quantum vacuum. Another avenue involves the search for signs of a multiverse, multiple, perhaps infinite universes existing alongside our own. Some theories propose that our universe's birth was just one bubble in a vast cosmic foam, each bubble potentially arising from nothing through quantum processes. If such a multiverse exists, it might leave subtle imprints, like specific signatures in the cosmic microwave background or unique gravitational wave patterns that we could detect with precise instruments. Advances in particle physics also contribute to this quest. Experiments at facilities like the Large Hadron Collider attempt to recreate conditions similar to those fractions of a second after the Big Bang. Although we can't recreate the universe's origin directly, understanding high-energy particle interactions and the properties of the quantum vacuum can shed light on whether nothing can give rise to something. Furthermore, some researchers explore the mathematical consistency of various models, looking for clues in the predictions they make, such as the nature of space-time, the behavior of quantum fields, or the formation of primordial structures. While these steps are indirect, they serve as vital tests that can support or refine overarching theories about the universe's emergence from nothing. Though tricky and still in many ways theoretical, these experimental and observational strategies are vital tools in unraveling one of humanity's most profound mysteries. How does something come from absolute nothing? Grappling with the concept of nothing doesn't just challenge our understanding of the universe's origins, it's a profound invitation to reevaluate what we consider the very fabric of reality. If nothing isn't simply the absence of everything but a state rich with quantum potential and fluctuations, then our classical ideas about existence become just a slice of a far richer picture. It pushes us to see reality not as a static backdrop where events unfold, but as an intricate dance woven from the energetic tremors of quantum fields. This perspective has mind-bending implications. For one, it blurs the line between existence and non-existence. If the universe can arise from a quantum vacuum that seems empty yet brimming with possibilities,